All right, guys, let's go ahead and start. So Rotary Motion, we already started it, and we're going to continue it. By the way, put in your calendars, we're going to have a quiz on Wednesday.
What?
It's a quiz, relax. We still got Monday when we come back, right? It's an assessment. It's a long quiz. No, because the test is the whole period. This is only going to take half the period. So we're going to do stuff the first 45 minutes, and then the second 45 minutes you'll do your test, your quiz.
We're going to do it first.
We'll do,
it's a long quiz.
Well, because of the 45 minutes. But I'm only going to ask like 4 or 5 questions.
Oh.
You know?
That's scary.
4.
That's so bad.
No. Why? They're going to be basic questions. We're not going to do advanced, like super crazy questions. All right, here we go, guys. Yeah. Rotary motion. This. Yeah, since everything we talked about this week, which has just been rotary motion. All right. Circumference of a circle is 2 pi r. Everyone knows that, I hope. Yeah, turn it on. So circumference of a circle is 2 pi r. And I have it in here. So that means that if I go 1 revolution, yes, I also travel 2 pi radians, but that's where that formula comes from. That's where the 2 pi radians come from. When you travel 1 revolution, you're going to travel this distance. So if this were a wheel, and I were to do 1 complete revolution, 1 complete revolution is 2 pi r. I didn't start, miss. I just started. Look, we haven't done any work. I let the record show that I just got an angry face. I'm recording on YouTube, so.
Oh, really?
Yeah. So now you're on YouTube, miss. I hope you're happy now. All right, here we go. Cool or not cool? All right, so you can use this information if you want, but I noticed that the last 2 pre-cal classes have not been using that information. They've been doing it like this, which is fine because you guys learn from me, but I would like for you guys to use your logic. So look, it says, look at example 1. What is the linear velocity of the wheel spinning in 5 revolutions per minute with a radius of 20 inches? So let's answer that question first. Here's how everyone has been doing it. They go like this. Chav, I say 5 revolutions per minute. And then you told me yesterday, Chavez, that 1 revolution contains 2 pi radians. And then I'm like, yeah. And then you said that in 1 radian, that just means radius. And I'm like, yeah, of course, that's what a radian is. And then you wrote 20 inches. And then you're like, yeah, well, there it is. There's my linear velocity in inches per minute. That is fine. That is perfectly fine. What I'm trying to say is that you don't have to do an extra step. If you want, you can do this. Don't write this down, just listen. I'm going to write it in blue. If you want, you can just do this. 5 revolutions per minute. And in 1 revolution, I know that the distance I cover is 2 times pi times 20 inches, because that's what circumference of a circle is. So that's what I'm trying to say, that you don't have to do what's in red, but if I've seen what you guys have been doing this morning, everyone's just been doing what's in red instead of in blue. That's fine with me. It doesn't matter to me, as long as you are comfortable with it. Cool or not cool? So which one do you guys like better, red or the blue? Red? Okay, guys. All right, that's fine. Okay, take your calculators. Do you guys have calculators with you guys? And then just go 5 times. If you want to leave it in decimal, cool. If you want to leave it in terms of pi, that's fine as well. Yeah, you can grab some calculators over here. Here we go. 5 times 2 pi times 20.
Wait, can I have one too?
The pi on the TI-84s is on top of the division sign, where the caret is at.
Oh, I see it.
There it is. There's my answer. That's my linear velocity. And then it proceeds to ask me, what is the angular velocity? How many different ways can we express the angular velocity? Angular velocity is just a measure of rotation. So angular velocity is, the first one I see is this one. So I'm going to say 5 revs per minute. That's not the only way you can say it. I'm going to put ... I'm not going to put the number, guys, because then I have to calculate it all the time. I'm going to say you can say it in revolutions per second. ... You can say it in revolutions per hour. ... If you want, you can say revolutions per day, but that sounds kind of funny. Why would you do that? You can do radians per second. comma, or dot, 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 comma, dot, 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 radians per minute, dot, 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 radians per hour. I think these are the acceptable ones. And of course, you can always put any unit of time, but it stops making sense if you say per day, per whatever, you know what I mean? Because we're talking about at that moment, so you usually want to have it short. Cool or not cool? Cool. All right. Does everyone know what an axle is? It's okay to say no, guys. In case, okay. So an axle. In your vehicle, you have an axle, but that one has gears inside of it. So this is an example. It's a bad axle, of course. Pretend this was made of metal, and I have a big wheel here, and a little wheel here, a big one here, and a little one here. If this rotates one time, do both of these, the big one here and the little one here, rotate one time? Now think about it. Just rotate. Yes, it does. If I rotate one time, the big wheel and the little wheel are going to rotate one time as well. So the angular velocity is the same, but the linear velocity is different because the big wheel is going to cover more distance than the little wheel. Does that make sense to you guys? Yeah. Perfect. So for right here where it says two rotating objects connected by an axle have the same angular velocity. So this is notes for you. So I'm going to try and draw an axle. I'm going to put it out there, guys, that I got a D in art. I don't know. I told you guys, right? So yeah, I did. I got a D in art. Hey, don't ask questions. Well, tell that to my professor.
Oh, in college?
Yeah, in the university. I wouldn't get a D in high school. High school's a joke. So is university too. Huh? Yeah, I needed an elective, so either an art or music appreciation or something like that. I got a D, and when my advisor looked, I guess the D's technically passing, right? And when my advisor looked, he was like, "You got a D in art." Like, yeah, I know. And he just said, "All right, just keep going." So I guess if I would have gotten an F, I would have had to retake it. But because it's not part of my major, they were like, whatever. I have a perfect 4.0 GPA in math, guys, so it's okay. All right, anyways. So look, I tried my best to draw an axle. As you can see, my drawings suck. So maybe that's why I got a D. There's a big wheel here, little wheel here. Both of them are spinning, I guess, I can't even tell the way. So if I do one rotation on that axle, both of them rotate by one revolution, if I rotate it one time. Does that make sense? But the linear velocity is different. Cool or not cool? Cool. All right, this one. Two objects connected at their rims have the same linear velocity at their rims. Well, yeah, look. That happens all the time, guys, with gears. Man, my drawings suck. So there it is. Two circles or two gears connected. Do you guys see that little blue dot? Yeah. So look, because pretend there's gears here. I know the way it looks right here. It doesn't look. If there's gears here, whatever distance this is traveling the same distance. Notice I said distance, not rotation. So if this is going 10 centimeters per second, then this little guy is going 10 centimeters per second. Yeah, same linear velocity, but the angular velocity is different. If this guy does one revolution, this guy's doing a whole bunch more than one.
That makes sense.
Yeah, cool or not cool?
Yes.
So perfect. And then there's one more situation which we already talked about, but I just didn't put it in these notes, so my bad. Put a little slash through there. And then one more situation 3, I guess, is if I have two of these gears or whatever connected by a belt or a chain. And we kind of already talked about this, guys, because we did the bike problem. And my circles aren't really that good. Again, my D's coming out here with my art sucks or whatever. All right, anyways. In this case, look at this belt. That belt, if this little guy drives that belt, that means that both of these have the same what? Perfect. Linear velocity, but the angular velocity is different. Oh, so I got a D in art?
No, I thought you have a DNR.
I don't know why.
I don't care. I'm bringing you back. I thought you were waiting for spinners.
Oh,
Because you have your thing back there. I'm like, I like it, Charles. But now I have a fashion idea for you. Do you like how to make this happen? Okay, back to the important.
No, we're good.
For the title of your YouTube video, you better say featured Miss Grenada.
Hey, Miss Brahida, you're gonna come out on YouTube. I'm gonna show you this. I'm gonna bookmark it. I can't tell the time, but I'm gonna come. Okay, yeah, we'll show you this. All right. So here we go. So same linear velocity, different angular velocity. Cool? Cool. So put that in there somewhere. All right, let's go to the next page. Or turn the page, right?
It's okay.
Oh, yes. I'm back. I'm back. Look. No, that's okay.
No, I think it's old.
All of them? Okay, I'm gonna go slow. Okay, like really, really slow. I think you're confused because we're just talking about ideas and we're not doing any calculations yet. So as soon as we start calculating, you're gonna see it's gonna be pretty easy.
Wait, so linear distance compared to time, right?
Yeah, linear is distance divided by time.
And then angular is the degree?
Angular is degree or spinning, anything that has to do with rotation.
Okay, and so how come the first one is it angular because they're moving at the same time?
It's angular because they're connected by an axle. And because they're connected to a fixed axle, if the axle does one revolution, everything that's connected to that axle is doing one revolution. You know what I mean? So, I should have brought straws, and then straw could have been an axle. I could have put a big circle on one end and a little circle on the other. Man, that should have been, see, but I didn't have an artistic mind, so I couldn't have done it.
Wait,
Yes.
is the first one, or just the name that the linear velocity, are you like just looking at one specific point?
Yeah, I'm looking at the points on the rim for linear velocity for number one. Of course, if you're at the center, you haven't traveled any distance. Like if you're right here where this blue dot is at. If you're where that blue dot, you haven't traveled any distance. All you're doing is spinning. So at the center of anything, the linear velocity is 0.
But with the linear, I'm trying to think about it like little like gears. Like it's kind of funny, but I keep on thinking like the Mickey Mouse gears,
Mhm.
where it's like they're moving together. But then how do they have a different angular?
They're different sizes.
So then
Not for number one. Okay, number one does not. Number one has the same angular on this one. Look, this is my axle. This is a big circle. That's the rectangle.
I think I just don't understand the difference between
Angular is just to do with rotation. That's all it is. So if I were to put a big circle here and a little circle here, and I spin this one time, both of them spin one time. Both of them do one revolution. But which one covers more distance? Well, the one with the big circle covered all this distance, and the little circle just covered a little distance. Does that make sense? All right, check this out. I'm gonna go slow, guys. The two pulleys are connected by a pulley belt. Oh, okay, thank you. Letter A, bless you. The small pulley has a diameter of 10 centimeters. So if the diameter is 10 centimeters, that means the radius is 5. I might need that. And rotates at 100 revolutions per minute. All right, so this little guy is rotating how fast, Miss Tift?
100 revolutions.
Perfect. That is, what is that? Is that angular or is that linear? What did you say? You said angular?
Sure.
It is. Why is it angular? Because it's talking about rotation. Anything that has to do with rotation is angular. So that means revolutions. That means radians. If it says spins, 1 spin per second, all those are different ways to say angular velocity. Cool? All right. Find its angular velocity in radians per second. Again, they're still asking for angular velocity, but they want it in different units now. Do you see that? Okay.
I was able to understand it as I thought of the track fields, how like if you're inside, you're going to be running motion.
Yes.
I like that.
Yeah, so if you're in a track field and you run closer to, perfect. All right, you guys ready? Here we go. I'm gonna write 100 revolutions per minute. In one revolution, how many radians do I have? 2 pi. So there it is. I cancel the revolutions and I have radians per minute. And then I say, in 1 minute, how many seconds are there? So there it is. Minutes cancel out. And then you just take your calculator and you go 200 pi divided by 60. And you get 10.47. 197,551 radians per second. If you want to have it in terms of pi, you can. Let's see, 200, 200 divided by 6, that's 100 over 200 divided by 60. Math, fraction, enter 10 power 3. If you want to have it as 10 power 3, that's fine. How do we feel right now? We feel okay? Focus, miss. Okay. Next one. Find the linear velocity of a point on the rim of the 10 centimeter pulley. Okay, we're looking for the linear velocity of a point on the rim, which happens to be touching the pulley. So here we go. I'm going to say 10.4719751 radians per second. And in 1 radian, what's my radius? 5. And there it is. You have centimeters per second. So I take that number that I got earlier, and I'm going to multiply by 5. And there it is. 52.35987755 centimeters per second. Put units on everything, please. Are we still okay, guys? Tipped? Are we still okay? Okay, what's up?
Why do we use a radius?
Oh, because I want to know what my linear velocity is, and I know that in 1 radian there is 5 centimeters. You don't have to go that route. You could also start from revolutions, and you could say in 1 revolution is 2 times pi times 5 centimeters. It's the same thing, though.
Put that as a fraction.
Yes, you can. You can put that as, let's see, 10 times 5, 50 power 3 centimeters per second. If you want to leave it in terms of pi. How do we feel so far? Cool? All right, letter C. Find the linear velocity of a point on the belt connecting the 2 pulleys. Well, if the point on the rim is 52.35, is that also the speed of the belt? Yes, it has to be the same, guys. 52.35987755 centimeters per second. It has to be the same. How do we feel so far? Tiff, are we pretty good right now or no? All right, letter D. Find the linear velocity of a point on the rim on the large pulley. Well, they're connected by the pulley. So then that means that linear velocity has to be the same again. This time they give me some information, which has a diameter of 30 centimeters that might come to play. So I come back to my little figure and I write 15. All right, here we go. Letter E. Find the angular velocity of a point on the rim of the 30 centimeter pulley. There's 2 ways to do this. So far, everyone, well, I guess I'll let you guys vote. Do you guys want me to do this by converting the centimeters per second to angular velocity, or do you guys want me to do a scale factor? Okay, let's do the centimeters per second into angular velocity, right? Because you guys are asking, what's scale factor? Okay, does everyone agree? I guess before I continue, guys, does everyone see that blue dot? Does everyone agree that blue dot is going 52.3598775455 centimeter per second? Okay, I'm going to convert that to angular. Here's how you do it. I write that speed, 52.35987755 centimeters per second. And then I'm looking at that circle and I say, in 15 centimeters, there is 1 radian, because that's my radius. Does that make sense to you guys? So I'm going to write 15 centimeters, 1 radian. And check it out. Centimeters cancel out and you just have radians per second. Yes?
So, in this situation, are the radians the same as a revolution?
Yes, because 1 revolution is 2 pi radians. If I want to convert this to revolutions, you can.
So then, how come you're using the radians?
Oh, because they didn't specify what units for me to use, so I'm just doing whatever I think is easiest. Oh, because that's my radius. 1 radian is your radius. You know what I mean? Okay, so here we go. And I get 3.49 0.065853, and this is radians per second. All right. I do not want to make you guys robots. I want to make sure that you guys know that you guys are super intelligent and super smart. You could have done this another way, and look, it's going to work. This radius is 5 centimeters. This radius is 15 centimeters, correct?
Yep.
My scale factor is 3. What does that mean? We're smart guys. What does that mean? That means every time this guy does 1 revolution, this little guy is doing 3. They want to know the angular velocity of this guy, right? So I already have radians per second. I can actually do it however I want. I have revolutions. I can take that 100 and I can divide it by 3, so 33 and 1/3. Or I can take this radians, because that's my answer in radians. I bet you if I take this answer and I divide by 3, I bet you it's going to be the same. Do you guys see that?
Yeah.
So check it out. I'm going to scroll up until I get to the 10 point whatever. Where are you, buddy? There you, nope, that's not it. There you are. And I'm going to divide that sucker by, did I say 3?
Yeah.
3. And look at that. It's the same digit per digit.
Awesome.
Now, real quick, guys, because I want you guys to be smart. I don't even know where the question is anymore.
Down there.
Down there. All right. I want you guys to be really smart because I want you guys to have options. Does it tell me what units for me to use for angular velocity? No. If you feel, so especially like Ms. Smith, you like revolutions better, right? The radians. If you feel, if your heart tells you, oh, I want to write it in revolutions per minute, go ahead. It's fine. In revolutions. Cool? It would be 33, I think, and 1/3. All right. How do we feel so far?
What is a radian?
A radian is literally what's the radius.
How does that look like?
If you want to convert that to revolutions, that might help you better. So that translates to 33 and 1/3 revolutions per minute. So it's doing, let's see, if it's doing 30, so that means it's doing almost, so you're doing like half a revolution a second. So that 3.49 radians per second is like almost half a revolution per second. Does that make sense? So yeah, sometimes the revolutions per second makes more sense than, remember that 1 revolution is 2 pi radians? So half a revolution is pi radians, 3.14 radians per second, so there's a little more than half a revolution. Because 3.14 is pi, right? So it's a little more than half a revolution. Does that make sense? Is it clearing up in your mind there? Okay. All right, letter F. Good questions, by the way. Keep asking. I want you guys to. All right, ready, Ms. Tiff? Find the angular and linear velocity of the point at the center of the 30 centimeter pulley. Okay, let's do the easy part. Linear velocity. Linear velocity at the center. Have you traveled anywhere? No. Velocity, put units, 0 centimeters per second. If you want to put miles per hour or whatever, that's fine. I mean, because technically you're still correct. It's 0 miles per hour. You have, as long as you put units of distance divided by time. Okay, angular velocity. Is it the same all the time? Yes, it's always 3.49. If you want to convert this to revolutions, that's fine. And there it is. How do we feel so far, guys? Okay. We're going to talk about this. It really helped out. Like you should have seen it. It was like day and night. Yeah, yesterday when we did this, I just gave it to them, and there was so many questions. And then today, I actually slowed down and decided to talk about it, and there was not that many questions. I went like 5 minutes. We're going to do an ask and answer.
She looks like a baby. She looks like what's that baby?
Maybe I'll get one soon. I just don't have enough time. All right, we're going to talk about this real quick. What's up? I didn't give you one? Oh, yeah, everyone has been able to finish. You'll have enough time, I think. If worst case scenario, let's say you don't have enough time and it's Friday, I want you to have fun, you can go. All right, here we go. Let me close this guy down. Save. And, all right. All right, guys, so let's talk about this together really quick. We're not doing it together. We're just going to talk about it. So you guys ready? Let's follow along. 4 pulleys are connected to each other, as shown in the figure below. Pulley 1 is driven by a motor, so it's pulley 1 that is driven, at an angular velocity of 120 revolutions per minute. It is connected by a belt, I would underline belt, to pulley 2. Pulley 3 is on the same axle, I would underline same axle, as pulley 2. It is connected by another belt to pulley 4. The dimensions of the pulleys are, and then they tell you pulley 1, 2, 3, 4. Okay. So let's talk about this. Don't worry, we're not going to just look at the picture. Don't even worry about the words up here. Pulley 1 and pulley 2. Pulley 1 and pulley 2 are connected by this belt, yes or no? That means they have the same what? Perfect, same linear. So somewhere in here, put pulley 1 and pulley 2 have same linear. Somewhere in there, write it anywhere, doesn't matter where. Pulley 1 and pulley 2 have same linear. Does everyone agree?
Yes.
All right, now let's look at pulley 2 and pulley 3. Pulley 2 and 3, according to the literature, says same axle. So that means pulley 2 and pulley 3 have the same what? Angular. Write that somewhere. Pulley 2 and pulley 3 have same angular. Now look at pulley 3 and pulley 4. They're connected by a what? By a pulley or a belt. So pulley 3 and pulley 4, pulley 3 and pulley 4 have the same what? Linear. Does that make sense to you guys? All right, so now that we know that, see if you guys can tackle this together. I encourage you guys to talk about this and see how far we can get. And of course, you're free to ask me questions. So let's take care of this, guys. Am I going to talk about Rihanna?
Yeah.
I'm good.